All right, this is the Unit 2 Shells Guided Inquiry activity, and I just want to touch on some of the basic takeaways that we should have from this. Because again, the objective of this activity is to get us looking at, Bohr's idea of energy levels and how that applies to what the electrons are doing in the atom. And to take what he said about the hydrogen atom, which was very simplified because there's only one proton and one electron, and apply it to the other atoms, which again are more complicated. They don't follow that equation for finding the energy transitions for the electrons like we saw for hydrogen. But again, we can still talk about the idea of the principal energy level like Bohr introduced. And this gives us some data to back up and confirm our statements as we go into talking about the quantum mechanical model. So this is the Coulomb's law equation. Again, the F, the force, being the magnitude of the electrostatic force of attraction. And so typically we're looking at this in terms of explaining or describing the difference in attractions between the electrons and the nucleus in various atoms. So the larger negative value you get for this, that means the stronger the electrostatic attraction is between the nucleus and the electrons. And also that means the more difficult that electron will be to remove from the atom. So that's kind of the idea. As we look at these pictures, again, if we have, this charge, there's 2 times the positive charge. So this is like if I had a +2 times a -1 versus the -1 times -1. Well, obviously this value comes out to be twice the value when I have the 2 positives in the nucleus. When I am factoring in, though, this distance factor, well, again, the distance, notice, is in the denominator. So the larger the distance between the 2 charged particles, the smaller this force of attraction is going to be, or the smaller the magnitude of that negative force of attraction will be. And this is also squared. So again, you can factor that into your discussions about the relative effect of this distance on this versus on this scenario. So I'm not going to go through all the answers to everything individually because I think this part is pretty easy to see where these relationships are coming from with the forces and the particle charges. We do see that this larger charged nucleus in depiction 3 here, there's 3 electrons, 3 protons, and clearly the larger distance electron, that's going to be the one that's easiest to remove. Because again, if we look at that equation for the electrostatic attractions between this electron and the nucleus versus these 2, this one's going to be a lot smaller of a value because of that distance factor in the denominator. If we look at, it's not letting me go to the next page. That's helpful. Oh, there we go. There we go. Okay, so this, the perspective in the atom of why we do this energy scale the way we do is a little bit tough to kind of get your bearings on. But the questions on the second page have us looking at how should we be representing the relative amounts of energy. So we know that the ionization energy is reported as a positive value. That's the amount of energy required to take out an electron, the first electron from the atom. And so we have this equation for that. And we were asked which is at a higher energy. So the fact that I see the energy term written in on this reactant side means that we know that energy for the reactants equals energy for the products overall when we are looking at, a reaction, law of conservation of energy applies. So the reason this energy term is written on the left-hand side is that the energy of A alone does not equal to the energy of the electron and the ion. And so this extra energy term is added to the reactant side to make them equal out. So when I look down to, well, it's an endothermic process, right? We see the energy term on the reactant side. It takes energy. Energy has to be input in order to make an electron be separated from its atom and form the ion. So that, and thinking about it from that respect, requires an input of energy. You see the energy term on the reactant side, which is a characteristic of endothermic. So all those things together kind of give us number 5. So when we go to do the drawing on this graph, again, we saw the depiction before of the energy of the electron when it's in the atom versus when it's being released from the atom. And so the electron, when it is removed, we say that the energy is equal to 0. Let's see if there's some way that I can mark up this paper. There we go. We'll put that there. So this is my energy when the electron is removed. That's what we've defined it as. It's how we've seen it depicted in our previous diagrams. And so likewise, when I'm looking for the what must the energy, so this is the energy of the electron that's been removed in the ion. This 1312, negative 1312, I'm going to put that down here, roughly, there we go. So this difference between the two should be the 1312, right? Because I had to go from the energy and the electron, we describe it as having some sort of negative energy, and we could actually calculate, there's a version of, it's not quite Coulomb's law, but it's a version of that equation that has just d in the denominator and some constants that gives us energy. And that opposite charge, again, gives us a negative amount of electrostatic energy. So the electron in the atom is at this lower potential energy, and then when the electron's removed, we're up at 0 energy. So this is where we should have had our markings. I'm sure that you figured out they should have been 1312 kilojoules apart, but we're, the removal is right here. So this should be the ion and your electron, and this down here is the original A in your depiction. All right, moving on. Okay, so the energy difference again is that ionization energy. And so if we're looking at this trend for hydrogen and helium, well, if you just go along with, what the numbers seem to be doing, 1312, 2373, you had to make a prediction. You might guess that these ionization energies are going to be increasing as you go from hydrogen to helium to lithium. Then it says, based on comparisons you made in question 2, how would you explain the differences in the values of the first ionization energy for hydrogen and helium? So again, we looked at the difference in charge of the nucleus. As far as we know, the electrons are going into the same place, the same relative distance. So again, all of the things being equal, the distance term is the same. The distance, let's go back to this. All right, so looking in question 2, all right, so this, B versus A, obviously the larger charged nucleus, it's going to be more difficult to remove an electron from the same distance than the lower charged nucleus, an electron at the same distance. So that's what that question's getting at. And then we are looking at this graph, energy diagram below, first ionization energy for hydrogen and helium, so put those on here. So again, the first ionization energy, or the energy diagram, again, this is the amount of energy that, this positive value is the amount of energy that we needed to pop the electron out of the atom and get to 0 energy in reference to the nucleus. So we're going to depict these as negative. So negative 1312 goes right here. Do that right there. So that's for the H. For the helium, we said it was 2373, so that's going to be negative 2373, and we'll put that right here. So again, if you're looking at, it says, how does your diagram illustrate the relativities? So notice, again, this depiction, the reason we're doing it in the order we're doing it is because, the lower the ionization energy, that means that the closer it is, that electron is to being able to be removed, and the less energy it takes to take it out. So this distance from here to here gives me the relative ease of removal. So it's, this electron in helium is way more strongly held in closer to the nucleus than these ones in hydrogen. So that's also another reason for depicting this the way that we do. Looking at lithium, again, just making a prediction. So I kind of already did that with looking at these numbers. It kind of looks like the numbers are increasing. So you might off the bat say, well, I think it's going to be somewhere down here. But hold on, let's look at the next page. It's actually 520. So when we look at 520, we'll add that to our graph. Again, the trend might have made us think it was going to be down here. Maybe you remembered what the trend was from previous years of chem, but this is actually where it belongs. So let's look at why we have an increasing ionization energy, and then next thing we know, we've got this way smaller ionization energy. Well, looking back, it actually references question 2, but more likely question 3 has a depiction of actually what lithium looks like. And, we'll get into in the future questions looking at how many electrons are in each energy level. But there's 3 protons in lithium, so that's what this is representing. There's 3 electrons in a neutral lithium. And notice our first 2 electrons are actually in this closer distance position, and the third electron is out here. And so again, in comparing, why do we see that much lower ionization energy? Well, again, we've got this higher charge in the nucleus, so that Q value is going to be, +3 versus the -1 of the electron of interest. But this distance is like 4 times the distance, and that's squared. So notice that drives this force of attraction. Because that distance is so great, it drives that force of attraction down substantially. The other thing also that we're going to eventually take a look at is what these extra negatives kind of blocking or shielding the pull of the nucleus from this outer electron. Those will come into play as well, but certainly this distance is the biggest factor in looking at that difference in ionization energy. All right, keep going. So to remove a second electron, well, notice if I go back to this diagram, if I remove a second electron, where am I taking it from? So this one's already gone away. Well, now I'm dipping into these ones right here, which is very close. So the attractions between this set of electrons and this nucleus is a much greater, stronger attraction than way out here. And so then we're going to notice it's very, very difficult, requires a huge amount of energy to remove those electrons. All right, so if we see this pattern for that whole third period of elements, that's the second period of elements. There's the pattern. And it says, explain the trend. Well, again, we just saw the electrons in comparison to the nuclear charge. And we see that the nuclear charge from element 3 to 4 to 6 to 7 to 9 to 10, nuclear charge is increasing. Again, we kind of haven't been told about where exactly electrons are going into which energy level, but we have no reason to believe that we're doing anything but going into the same energy level, meaning at the same roughly relative distance as the other electrons that are already there. So as that nuclear charge increases, right, that numerator value on the force equation increases, we see that these are more and more difficult to remove and have higher and higher ionization energies. All right, let's keep going. Okay, so making predictions. Well, let's see. What should we have predicted? Well, here's the pattern. So it's increasing left to right. Notice that when we compare to the previous period, so this was 13, 12, 23. So hydrogen, notice lithium's right underneath it. So let's look at lithium. Lithium's 520. So we went from 1300 to 500. The helium, which is, well, probably we should compare the neon, which is right underneath helium, but notice that's 2000, so that's down from what we had with helium. So looking at the trend, it's increasing left to right across the period. However, this period seems to have lower ionization energies than the one before it. So if I had to make a prediction based on that, well, these ionization energies, I would say, are increasing left to right, but they should be less than the ones in the previous period. So if you had something along the lines of like, around 700, around 900, around 1100, around 1450, around 1700, in that ballpark, again, increasing left to right, but less than the previous period. That seems to be the trend that we've noticed from looking at periods 1 and periods 2. All right, so then we look at 16. So rounding out, what do we know about shells? Again, the shell is kind of like the energy level. So this is all the data that's plotted here. But notice that there are how many groups? Well, we've kind of got this, can I circle these? We've kind of got this as a group down here. We've got this kind of as a group, and see how there's kind of like a difference in these segments here. So this is a group right here. So we've got 3 groups or shells. Oh good, it's going to let me circle it. There we go. So this is a group right here. This is a group right here. And this is a group right here. And again, you can kind of see the groupings. So I've got 3 levels or shells. And again, these are all around, although there's a difference in the amounts of energy, they're kind of in a similar grouping together. And these are definitely way, way different in energy. Indicate the number of electrons in each group. Okay, so this has 8, this one has 8, and this one has 2. So notice the greatest, and again, these are plotted with negative values as represented in the where they'd be in terms in the actual atom itself. The greatest negative value means the most difficult to remove. So most difficult to remove, we've got 2, so that would imply closest to the nucleus. These we've got 8, and then these we've got 8. So let's see what else we're asked. It's question 6, page 6. What represents the average energy for each group? What do these lines represent? So what we're really looking at is the idea of Bohr's energy levels. And we know that things are getting a little bit more complicated the more protons we have. We know that for each of these electrons as they're removed, we've got fewer electrons and the same number of protons, so that's why there's this varying amount of energy as we continue to remove electrons. But there's a clear differentiation in this group. So again, if you're asked to label the average, so that would be just kind of in the center here, just get the value. So just notice that if I just centered this group and read over, they would be like kind of a different overall average. And that, when we look at our PES data in the next class, will become more evident what that the differentiation in those levels. How would you describe the relative energy separation of these levels? So clearly there's a huge, huge, huge difference between this first energy level closest to the nucleus and these. So first energy level, second energy level, third, but these are very close. And so this is going to be something very interesting for us to start to take a look at when we get into our next activity. But again, it tells me the relative energy of these, this group is way, way, way lower energy, more difficult to remove from the atom than these that are at higher energies and easier to remove. And lastly, let's see here. An electron from which level requires the least amount of energy to remove? So obviously the ones that were higher on the graph, closer to 0, those were easier to remove. And so we would imagine those to be further from the nucleus. So again, you can write up your summaries. You should have written up your summaries already, but that is the shell activity in a nutshell. Oh yes, she went there. So the shell activity, again, we're looking at the energy levels. We can definitely see from this data, even as we pull one electron out at a time, the varying amounts of energy. There's a clear difference there's some different levels of energy required to remove. And so there's confirmation here that we have some different energy levels. In the next activity, we will look at the subshells making up each energy level.